Okay, so yeah, let's get started. I think the recording is working. Yes. Yeah. So today, what we are going to do is last week we stopped at hash commitments. I think we didn't do hash commitments fully. We were started with some kind of hashing and what are the properties the hash will. What are the good properties of the hash will help us in that. So I will start with hash commitments and again revisit the Merkle trees and why a Merkle tree, which is a cryptographic data structure, is quite important in the Bitcoin. We'll see what are the advantages it will offer and things like that, and then we'll move on to storing and using cryptocurrencies. Especially, this is quite important when you have a lot of coins or when you have a huge wealth. It is no more we will look into different strategies, how actually you can have cold storage and hot storage and those kinds of things. So hot and cold storage. Cold storage is for storing huge amounts of coins and in a secure way so that nobody else can hack it and steal the keys and things like that. Hot storage is for spending small coins, like keeping your change in the wallet, right? Something like that. And then we look into the cryptographic wallets. So you can say the cryptocurrency wallets. These are a specific type of wallets. You can say software wallets, which actually store your coins. And there are different types of wallets like deterministic keys, or whether they use deterministic keys or whether they use non-deterministic keys. That is another thing. So we'll look into the wallets. And then we will also look into the mnemonic code generation. Mnemonic codes are something easy to remember phrases for the public keys, public and private keys, right? So this is one of the important aspects because you never remember your private key by the numbers. But on the other hand, you will remember your private key and all the important information using some bits of what you can say phrases and things like that. So a set of phrases, something like that. So that's what we will look into, and then we will also look into hierarchical key generation. What kind of strategies do we need to use, especially when we want to generate thousands and millions of keys, right? So again, one of the things which we argue is you need to use a pair of keys for each transaction because that will give you anonymity and other kinds of things. So especially if you need to deal with a huge number of keys, so what are the good strategy to store the keys, right? So for example, let's say that you need 50,000 keys, then it doesn't make sense to create 50,000 public keys and 50,000 private keys and store them safely, right? Because it can be easily hacked and other kinds of things. But on the other hand, we look into a good strategy, which is a hierarchical key generation, how keys can be generated using some information and things like that. So, and again, hierarchical key generation will also need elliptical cryptography. I also have few slides about elliptical cryptography. We don't use RSA or the public key RSA algorithm in Bitcoin and other cryptocurrencies. And rather than that, we would use a elliptical cryptography, which is another asymmetric public key crypto system, which is much stronger than the RSA. So I have a few slides and a small video for explaining the elliptical cryptography, and we will look into the hierarchy generation. And then I put, there are still some more important aspects like the extended or hardened hierarchy key generation. For example, that will be useful in very scenarios. For example, you want to generate keys using the public keys rather than the private keys and other kinds of things. But I put those slides as optional because it goes a bit more technical and things like that. And there is also splitting and sharing of the keys. So for example, if you have a private key you can split the key into multiple parts. It's not splitting means it's not taking the bits by bits, but you can split the key in such a way that you can split the key in 7 parts in such a way that you can have any 4 parts. Whenever you can have the 4 parts, you can reconstruct the private key. So this is called Shamir key threshold encryption. So this is a better way sometimes if you want to store your private key at different locations where you can only need a subset of the keys to reconstruct the whole private key. But that is also an optional thing. I put the slides. Again, I will leave around 10:30. I have to leave around 2 o'clock in the Indian time, and yeah. So let's quickly go through the slides and things like that. Okay, we were discussing about the hash commitments. So I was saying that hash commitments offer a very good functionality. And this is one of the important concepts which we frequently revisit in many cryptocurrencies and blockchain, right? So we need to understand a bit more easier. So let me do one thing. I found a small video which can explain the
This video is about commitments.
Can you hear the voice from the video?
Yes, sir.
Okay, yeah. Let us watch.
Commitments are a building block in cryptography that are...
Sorry.
This video is about commitments. Commitments are a building block in cryptography that are used for various cases. They are a digital analog of a safe. Let us give an example. Here we have Watson and Sherlock. Sherlock wants to play the game called Think of a Number. He tells Watson to secretly think of a number without revealing it. Then, Sherlock guesses the number and he wants to check whether he guessed the number correctly. However, both parties can be dishonest, so they want some guarantees. Sherlock wants that Watson should not be able to change his initial choice. Watson, on the other hand, wants that Sherlock cannot know his initial choice. How can they do that? This is a typical application for a safe. Watson takes the safe, writes his number on a letter which he puts inside the safe, and closes the safe with the key. Watson gives the closed safe to Sherlock, but not the key. Now he has committed to the number. Watson cannot change it anymore, since the safe is in Sherlock's hands, but also Sherlock cannot know Watson's number, because Sherlock cannot open the safe. Later, after Sherlock guesses a number, Watson gives the key to Sherlock so that he can open the safe, and check what the initial committed value was. The digital analog of this protocol is called a commitment scheme in cryptography. More formally, a commitment scheme is a protocol between two parties who do not necessarily trust each other. We have 2 phases: the commitment phase, in which the first party commits to a value, M, by creating a commitment, C, and a secret key, D. He only sends the commitment, C, to the second party, and keeps the committed value, M, and the secret key, D. The second phase is called the reveal phase, in which the first party reveals the committed message, M, and the secret key, D. Using the key, D, the second party verifies whether the committed message, M, corresponds to the commitment, C. The guarantees that the parties want are given as properties of the protocol. The protocol must be correct, which states that the verification process of an honest commitment should always succeed. And then we have the properties that we mentioned also in our example. Watson wants the protocol to be hiding. Hiding means that Sherlock cannot extract any information about the committed value before the reveal phase. Sherlock wants the protocol to be binding. Binding means that Watson is not able to change the commitment after the commitment phase. Is there a simple way of creating commitment schemes? How about using cryptographic hash functions? A cryptographic hash should be one way. This means that it is easy to compute y as a function h of x, but it is hard to find an x given y. In addition, cryptographic hash functions are collision resistant, meaning that it is hard to find 2 different values x and x prime that evaluate to the same y. How can we use a hash function to create a commitment scheme? Say Watson wants to commit to a message M. The protocol goes as follows. Watson chooses a random value, R, concatenates R with the message M, and then computes the hash function h of m concatenated with r. The result, C, is the commitment. Why do we need a random number? Take a moment to think about it. The main reason is to hide the message, no matter how short and simple the message may be. For example, if one wants to commit between choices yes and no, then it would be easy for Sherlock to just hash both, yes and no, and see what the commitment value is. In the reveal phase, Watson will send both the message, M, and the random number, R, and Sherlock can then recompute the hash function. This makes the protocol correct. If both parties behave honestly, the verification process will always succeed. But what about hiding and binding properties? The main argument comes from collision resistance of hash functions. To change the commitment, one needs to find a collision. In principle, it is possible to find another input so that you have a collision. But if the hash function is cryptographic, then this is computationally too expensive. That's why we say that the protocol is computationally binding. What about?
There are also hash functions which are not cryptographic. For example, you use these hash functions in checksums and other kinds of things. But the hash functions which we use in the cryptocurrencies is cryptographic hash functions, and so that's why they are practically collision-free resistance, offer collision-free resistance and things like that. So yeah, we watch for some more time. And
The hiding property. Hiding is given by the one-way property of hash functions. Given the commitment, it is hard to invert the function. It is, however, not precise to say that the protocol is computationally hiding. For example, Sherlock might learn that Watson thought of an odd number. This is not inverting the hash function, but still Sherlock might be able to get partial information about the message. Hence, typically this construction is heuristically secure, but to prove the hiding property, the particular hash function needs to have additional properties. What about the case where Sherlock and Watson are computationally unbounded? Can we come up with a commitment scheme?
Okay, so yeah, we'll stop here, and then the video also talks about the other commitment scheme. It's called Feddersen commitment scheme, which is a much more advanced cryptographic commitment scheme. For the cryptocurrencies, it's just fine. We use cryptographic hash commitments. So this is what it says, right? Like, let's say that you have a message M, and you want to commit to the message. In this case, Sherlock and Watson, they're exchanging numbers, let's imagine. And then you create a commitment by choosing a random key, which is a number from the high mean entropy, what that means, taken from a big pool of numbers, trillions of trillions numbers, so that nobody can guess the key and things like that. And once you have the commitment, you can pass the commitment, and having the commitment with the other party will not reveal the message. Right? So that is the hiding property. Given the commitment, if you pass the commitment to someone, and if you don't reveal the key and message to them, and there is no way for them to find out what is the original message is. So that is the hiding property. And the binding property is that then once you made a choice, in this case, like choosing a number, later, since you are committed to it, later you cannot change it. So that is why these are the two beautiful properties offered by the hash functions. And then another important property, which is quite helpful, especially in the realm of cryptocurrencies, is the puzzle friendliness. What is puzzle friendliness? So let's say that we want to find a hash value with some restrictions or with some patterns. So for example, starting with few zeros and things like that. The puzzle friendliness property says that there is no easy strategy other than trying randomly. So that is the puzzle friendliness property. So it says that if you have a hash ID and X is the number you choose, and it belongs to some subdomain, and then there is no easy strategy for it. Let me use a simple example to explain what is a puzzle friendliness, right? So let me open the hash online hash tool. Just 1 second. Let me reshare it. Let me stop sharing and Okay, I will share my browser. So this is, so I hope you can see the browser, right? So this is a online hash web page where you can actually generate hashes, right? So for example, you can generate hashes for the files. You can drop a file and then it creates a hash value for it. Or you can, it can generate hashes for the, what you can say, for the text and input data, right? So let's choose SHA-256. SHA-256 is it produces 256 bit hash value. Let's say hello, and then it gives the hash value like this, right? So even if you change one character, and then the hash value will completely change and things like that. So let us say that I want to find a hash value starting with 10, right? So my hash value should start with 10. So what should I do? The puzzle friendliness property, it says that there is no easy strategy to achieve that. Only thing is you have to keep on trying with the different inputs, right? So I just put 1 and I got this hash value, which doesn't start with 0. So let's do like this. I'm just putting 111. Now you can see you get a 0 hash value starting with 0, right? But let's say that what happens if I want my hash value to start with 2 zeros, right? So the first 2 digits must be 0, right? Then you have to keep on trying, keep on trying, keep on trying, and keep on trying. There is no easy, the puzzle friendliness property make sure that there is no easy another strategy to find this out, apart from trying and trying and trying things, right? So it will take few hundred tries at least to get first 2 zeros and things like that. So let's get back to the slides. Just 1 second. Yeah, so that is the puzzle friendliness property, right? So there is no easy strategy to find out a hash value with predefined target space. So we call it as target space. And how do we use that? So for example, in case of Bitcoin, what we specify is, let's say that we are using 256 hash, right? And then we say that the first 16 digits, or you can say the 64 bits, because each bit is, this is hexadecimal format. Each digit is 4 bit. So the first 16 digits should be zeros, right? And if you specify this as the difficulty, so that means what I'm going to say is, whenever you create a block, the block hash value, you can say the block digest should be with the 16 preceding zeros, right? So if you specify constraints on the hash value like this, for example, with a target space with 16 zeros preceding and things like that, and there is no easy way to compute it, and you have to try and try many times, right? So this is the hash difficulty of the Bitcoin around 2014. And if you check the hash difficulty of the current states, it is many thousands of times, you can say. Now, I think it has the hash difficulty around 80 bits as preceding zeros. And that will make you to try at least few trillion times to get this hash value. So that's why people are competing. Everybody is competing to get this hash value with the specified format. And whoever gets this hash value, block hash value with this pattern, and they can make the block and things like that. So we will see all these things in the mining when we get to the mining. And we will also see a practical calculation how to convert the hash difficulty into the number of tiles you need to make and things like that. So this is another good property of the hash functions, which is really used in the cryptocurrencies. So finally, I just want to show you how a hash function works. So what you do is, remember, hash function thing can take input of any size, right? So it doesn't matter really. We have 10 bits or 100 bits or 512 bits and things like that. So what we do is, whatever the message size is, we split the message into 512 bits. So this is how the message is split into 512 bits. You might ask, what happens if the message is not a multiple of 512 bits? So then what we do is we just what do you do? We just pad the last part, right? Let us say that we have 10 blocks of 512 bits, and the 11th block is only 400 bits. Then we pad these 112 bits with zeros or some other number, and then you will get a 512 bit block. And then once you split the message, so what you do is you take a 256 bits initialization vector. This is called IV. So this is like a random number which you add to the, or you can say this is called salt, which you add to the hash function. And then you pass the salt and the message to the hash function, and it will output 256 bit. And that 256 bit is again used as an input for the second the second part of the hash function, right? So it keep on like that, and finally you get a happy 256 hash. Okay, any questions or comments? Yes, there is one question, it looks like. Okay, EC hash, I didn't get clearly what is C. Is the C language or?
So no, sir. The C which we are representing in the diagram, is it actually hash function? Like it's passing to another C and then to another C.
Oh, yes. So let me go back. Okay.
Yeah,
So
this
yes,
one.
this this is a hash function. Yes. The C is you can say the hash function. They use
Yes.
C to represent the collision-free hash function, right? So because you can again, the hash function hash is not a concept limited to cryptography. It was also used for checksums and other kinds of things. When it comes to the cryptographic hash function, C is they make sure that practically collision-free. As I told you before, collisions can happen, but that is over a long period, like maybe a few thousands of years. If you try, then you will produce a collision and things like that. So C is nothing but a hash function. Okay, so let's move on to the Merkle trees, right? So as I mentioned before, yes, go ahead.
Sir, but what's the use of adding a number with the message, sir?
Okay, yes, this one, right? You are talking about initialization vector.
Yes, sir.
Yeah. So initialization vector gives some sort of randomness, you can say, because in many functions, cryptographic functions, you need the message on one hand, and you also need some sort of the key or some sort of the randomness. So that's why you use this initialization vector as a piece of, we normally call it as salt. So that is added to create randomness so that it will give better things.
But if we'll pass it to cryptographic hash function, a hash digest is produced, right? So without the
Yeah.
number also a hash digest is produced. But how does it make
Okay.
unique?
It needs to, the hash function needs two parameters, right? The one parameter is the message which you want to digest. The other parameter is initialization vector, which is a salt kind of thing. So that's why you can see the first initialization vector, we use some random value. And when you get to the second stage, whatever the hash value which we get for the first part, we use this as an initialized vector for the second part. So actually the hash function requires two parts, initialization vector and the message. So that's why the hash value which we get from the each preceding step, it will be used in the subsequent But normally what you do is you don't see this initialization vector because it is internally dealt by the hash function. So when you pass the message, automatically the initialization vector is inbuilt by the function, and you only get the hash value out. Now I understood what you're asking about. Yes, the input to the hash function in the programming languages is just only the message, but internally the function will handle this initialization vector by itself. But when you look into the cryptographic terms, you need this initialization vector, which creates some randomness in the function and things like that. And this is also quite useful to guarantee the properties of one is the collision resistance and pre-image resistance and those kinds of properties, right? Like so that it plays a big role in those things. But when you use a programming language to generate hash function, you don't need to think about initialization vector, which is internally handled by the programming language hash function.
Okay, sir. Thank you.
Okay, let's move further. Okay, so we have seen the hash functions and things like that. And now let me introduce the Merkle trees. You might have heard about Merkle trees many times because of the cryptocurrencies especially, and the blockchain uses the Merkle trees. But Merkle tree is a cryptographic structure which was invented probably around 1980s and things like that. So they didn't think about the blockchain, but it's a beautiful structure. So what is the use of Merkle tree? So Merkle tree actually summarizes all the transactions. And so let us say that you have 4 transactions, right? You want to arrange these transactions in the form of tree. So you take 2 transactions in each step and then hash them. And then you combine them together and you build a tree like this till you get this root. And then in Bitcoin, so this is called the Merkle tree. I will show you why Merkle tree is quite efficient data structure and why do you use in Bitcoin, right? So, but in Bitcoin, what we do is you will do double hashing. So for example, let's say that we have 4 transactions and we want to build a Merkle tree for it. So we put 2 transactions together, and first we hash the transactions, double hash the transactions. And when we do that for the 2 transactions individually, and we take them together and we put them together side by side, and again we compute the double hash for it. So this is how the Merkle tree is built. So, and why double hashing? I think it was one of the design parameters, and I think Nakamoto and probably his team, they might thought that maybe double hashing is much better than the single hash. So that's why you take the hash of hash value so that you cannot easily find out the original message and things like that. Okay, why actually? What is the advantage of using the Merkle tree? Of course, it guarantees the immutability so that nobody can change the transaction and things like that. But there is also a very good property. For example, to verify a transaction, whether a transaction exists in the block or not. And remember, the transactions are organized into the Merkle tree. And you can verify whether a transaction exists in the block or not using the log n times. What is n? N is the number of transactions, and so this offers a lot of fast verification, right? So let me go back over here. So for example, in this case, we have 16 transactions, right? So we have 16 transactions. And then if I want to verify one, let's say the HK transaction exists or not, I'm interested about the HK. And I want to verify whether the HK exists in this block or not. So what I do is how many transactions, how many other hashes I need. So I need to log n, log 16. So it is base 2. So I need 4 hash values to verify whether a transaction exists in this block or not. So which hashes I need? So I want to verify HK. So I will need HL. If I have a HL, then I can compute this one. And then I also need HIJ, and then I will compute this one. And I also need this one, and also need this one. So to verify whether the transaction HK exists in the Merkle tree or not, or in the block or not, we supply 4 hash values, right? If you have the 4 hash values, then you can easily verify whether HK exists or not. So how much do we gain here? Rather than verifying all the 16 transactions, rather than comparing all the 16 transactions, we only use 4 hash values to find this verification. Of course, probably in this case, the gain is not a lot, because out of 16, again, you have to give 4, right? But on the other hand, let's see, because this is a log n verification function, let's imagine that you have 65,000 transactions, right? 65,000, it is 65,536, right? So this shouldn't be 536 because it is 2 to the power of 16, right? And then if the block contains 65,536 transactions, then you need only 16 hashes to verify whether a transaction exists in the block or not, because of the log verification thing, right? So that means you can verify a transaction with a ratio of 1 in 5,000, right? So that's why it offers a lot of very fast verification procedure. That's the reason why all the cryptocurrencies, no matter whether Bitcoin or some other things, they follow the Merkle tree as a default cryptographic structure to show the transactions, because of this fast verification technique. And many cryptocurrencies, even the Bitcoin as well, many times when a node want to verify whether the transaction exists in the block or not, normally some of the light nodes, you can call them a simplified payment verification, SVP nodes. So they don't download all the block. They just download the Merkle tree path, and then they do the hashing, and they verify whether whether the hash values matches or not. So this also offers a very fast verification technique. Any questions? Okay, so let's go further. Let's move on to the storage of the coins, right? So if you want to spend a Bitcoin, what you need is some information from the blockchain, public blockchain, like to which public key the coins were transferred, and how many coins, and other kinds of things. And then if you want to spend the coin, you need the secret key. We have seen this in the previous class and things like that, right? So when it comes to storing the cryptocurrencies, everything boils down to the key management, right? So basically, you need to carefully keep your public and private keys, then the coins are safe. Right? If you mess it up with storing the keys, then you will have big problems in the coins. So let us say that when we look into these the strategies for storing the coins, we look into 3 characteristics. So the availability. So availability means whether you need these coins to be available all the time, or how much availability you have. For example, if you have your key in your mobile phone, then it is always available with you, because normally you will keep your mobile phone always. So that is the availability. And the second aspect is the security. And security, nobody else want to spend your coins. So how secure is the storage, where you store the keys and things like that. And the third aspect which we look into is convenience. How convenient is that? Do we just, if the key is stored on your mobile phone, then you can just use instantaneously. But on the other hand, let's say that the key is stored securely on a computer, remote computer, where stored in a some safe or something like that. Then you need to go there and access the key and things like that. So the convenience is also another aspect which we look into different strategies. So based on the requirements, you have different trade-offs between the availability, security, and convenience. Right. So let's look into some of these strategies for storing the coins. So the simplest approach is store the key in a file on your computer. So now I'm talking about the public private keys and things like that, right? So as I told you before, the you have to store the private key securely, right? So you can store it on a computer, or you can store it on your phone, mobile phone, using a wallet and things like that, and which is very convenient. The availability, when it looks to the availability, it is available to you as long as you have the control over the device. So for example, as long as you don't lose your mobile phone, this is available with you. Similarly, if you don't lose your laptop, then it is available for you. The security is a bit limited, you can say. If the device is compromised, then the keys are gone and the coins are stored. So storing private keys in the local device, like mobile phone or your computer, is like keeping the money in your wallet or purse, right? So it is quite convenient because it is readily available for you, and you can easily spend the coins and things like that. But on the other hand, it is not that much secure because you don't want to keep all your life savings in your wallet, right? What happens if somebody steals the wallet? What happens if somebody compromises the device, either mobile phone or laptop, and steal the keys and things like that? So then all your life savings will be gone, right? So that's why we use different strategies for different purposes. For example, if you have some small coins, small money, and then you will use the simple strategies. But on the other hand, you have a huge amount of coins, maybe a huge wealth. Let us say that you life savings and your earnings and things like that. You will store them in a much more secure manner. As if you do, let's say that you have a huge amount of wealth. Let's say that you have 50 lakhs of money. You got it from your ancestors and things like that. You just don't want to carry them in the wallet. But on the other hand, you will go to a bank and put them in a fixed deposit and more secure way, right? So similarly, in the cryptocurrencies also, we do those kinds of strategies. So before going further, I was telling you about the wallets. So the wallet is nothing but a software. You can also have the hardware wallets. I think I have one slide about it. So most of the time, these are the software wallet, which you can install on your mobile phone or a computer and things like that. Basically, what they do is they take care of all the underlying key memory, key management. You don't need to generate keys. Automatically, they will generate the keys. And as we have seen last week, if you want to spend something like buying a cup of coffee and things like that, they will do automatically. They will create the change addresses and other kinds of things. So all these things is automated in the wallets. So you don't need to take care of the keys anymore. And that's why it is very convenient, the wallets. And how do you use the wallets? So remember, you need private keys, right? The private keys are the key to spending your coins. So rather than storing your private key, what you do is you will use some tactics to remember it. That is called the mnemonic code, which we will see later. So most of the times, wallets, they maintain all these things. You don't need to bother about the keys and things like that. And they also do one more thing for you. For example, let's say that you have coins spread over different addresses, and then they give you some sort of account-based feeling, right? So they combine all the values for which you have the private keys in the coins, and they sum up and show you that your wallet has 50 Bitcoins and things like that. So they also do these accounting things. Okay, so wallet software is good. So it provides very nice interface and things like that. Yeah, you keep separate keys for each coin. And whenever you spend some coin, they also create a pair of keys for the change addresses and all other things. You don't need to do all those things underlying. So this is how addresses look like. And you can also use QR codes, because QR codes is nothing but some textual input and things like that. So these are things. Okay, let's do you want to take a break, or should I continue with this elliptic curve cryptography? So I have a video again showing the elliptic curve cryptography. It will take maybe 10 minutes to deal with these things. So are you okay with me proceeding, or do you want a break? Okay, I don't hear anybody asking for a break. So should I continue?
Have it after that 10 minutes.
So yeah, we'll continue. Okay. Yeah, so let us continue. And I was telling you before, we don't actually use RSA public cryptography in the cryptocurrencies, but on the other hand, we use elliptic curve cryptography. This is another crypto system, you can say. And the RSA crypto system, it is built based on the prime numbers. What you do is you take two pretty big prime numbers, and you derive public and private keys doing some mathematical modulus operations. It's built on the modular mathematic, and then you do some operations and you get these public and private keys, which are connected. And but on the other hand, elliptic curve cryptography used a different system. It's called elliptic curve. So the curve looks like this and things like that. And it has some beautiful symmetrical properties. And we use those properties to generate public and private keys. And it is much more secure, you can say, in terms of rather than RSA. So that's why people will use. Let me first briefly explain what is going on behind the scenes, and then let us use this one. Yeah. So it actually, elliptic curve is nothing but you have this curve. So this is elliptic curve defined by a formula and things like that. And it has some properties. First one is the symmetry property, and it has two important operations: addition and multiplication. And addition and multiplication, these are nothing but the points on the curve. At any point of the time, if you draw a line, it will meet the curve not more than 3 points, right? So let me run this visualization. Okay, let me run one more time. Okay, so why do we use this curve? So for example, let's say that you have 2 points, A and B. I want to add A to A and B. So I want to compute the A plus B. So the way we do it is you can join A plus B, and you can draw a line going through these 2 points, and it will meet the point at C, right, at this point. And then you take the inverse, the image of it. So that means you just go down and look into the other part of the curve, and this will be the result of A plus B. Right. Similarly, let's say that you want to compute A plus C, and let me run so you draw a line between A and C, and then it will meet the curve here, the third point, and you take the inverse image, then that will be the A dot C, right? So we don't call it as addition because this is a elliptic curve kind of thing. So you can easily compute the additions and multiplications like this. Okay, let me go use this video. It explains very well what is elliptic curve cryptography and also compares with the RSA. So let's
Hey everybody, John Wagnon here with Dev Central, and we are coming to you today with a Lightboard lesson video. And in this week's edition of Lightboard lesson, we're going to talk about elliptic curve cryptography. So I'm just going to write ECC up here. Stands for elliptic curve cryptography. And so a lot of people are, talking about elliptic curve cryptography. What is it? How does it work? Should I implement it? Should I not? Whatever. And so we wanted to take a couple minutes today to talk about this thing. Elliptic curve cryptography has actually been around since like the mid-1980s. So it's been around for a while, but it hasn't really been implemented or used extensively, at least, until just recently. And so anyway, it's a public key crypto system type of cryptography, whereby in public key crypto systems, you have a private key and a public key. And the private key, you can encrypt data with the private key or the public key, actually, and then you decrypt with the other one. And so there's this notion of public and private keys, and elliptic curve cryptography is one of those. And so when we talk about public key cryptography, I want to write this up here. We talk about the notion of a trapdoor function, and this is the math function that kind of underpins the public key crypto systems. And in a trapdoor function, kind of the basics behind it is that you can take a given value, I'll call it A, and use the trapdoor function to get to another value, and I'll call it B. And going one way, you can do that very, very easily. But then if you start with the other value, say start with B, and then you want to get back to A, then it's very, very difficult to do that. So I'll put an X over that. I'll put a little check mark by that guy. All right, so again, trapdoor function, it's very easy to go one direction. It's very difficult to go the other direction. And so using that, and using that in the sense of a public key crypto system, you need some sort of a mathematical function, mathematical foundation, whereby you have a good trapdoor function to use for that public key crypto system. One that's used extensively today is RSA, and it's based on prime number factorization, where you take two random prime numbers, you multiply them together, you get this really big prime number, and then the issue is multiplying those together is very easy, which that's kind of that A to B level. But then to factor those out, coming back from B to A is very difficult. That's why that's kind of the really basic fundamentals of RSA and why it works so well today. One quick thing that I'll put on elliptic curve and RSA, I'll put ECC versus RSA right here. And so with a key size in elliptic curve cryptography, if I were going to put, let's say we talk about a 256-bit key size in elliptic curve cryptography, in order to achieve that same level of security using an RSA key size, you would need a 3072-bit key. And so you can start to see that this is one of the reasons that elliptic curve is so much
in cryptography is the key size plays an important role. So the bigger the amount of the larger the key, the larger the security the function can offer, right? So that's why you go with a very, very big, larger key sizes and things like that. On the other hand, if you have a larger key size, the computational time increases very significantly. So that's why you try to find a trade-off between the security and the computation time. So that is the reason why you choose a middle strategy.
Man today, based on its comparison to RSA, the key sizes are much, much smaller, but you get the same level of security. If we bump this up to 384 bits in ECC, you'd have to go all the way up to 7680 in RSA. So you can see that as ECC, keeps this small number of bits, RSA's got to get like huge in order to achieve the same level of security. This right here, I'll put a little TS by that 384. The reason I put that is that's top secret level information in the U.S. government. NSA and the other government agencies have said that elliptic curve 384-bit keys are strong enough to protect top secret level information. And so that's a, there's no way you would get that same level of protection with an RSA key at 384 bits. It's just not going to happen. So anyway, all right, so that's kind of ECC versus RSA. But again, what is ECC? Kind of how does it work? What's the magic behind the curtain, as it were? So what I'm going to do is take you through kind of a bit of an example of elliptic curve cryptography, and I'm going to draw a math graph here, kind of a math function, where this is the x-axis and this is the y-axis. Alrighty, so you have this is your normal, you remember back to algebra or whatever, and you're doing your math functions. And so we're going to draw an elliptic curve on this graph. And the elliptic curve has a few interesting characteristics, and I'm going to do my best to draw an awesome one right here. So we're going to come like this, and that's not too bad. Okay, a few things that the elliptic curve has is that it is symmetric about the x-axis. So here's the x-axis. It looks the same on top, and it's like a mirror image on top and bottom. Symmetric about the x-axis. The other thing is that if you draw a straight line through this curve, it will intersect the curve in no more than 3 points. And so if I were to take a point right here, A, and I were going to draw a line through it, it would hit it in another couple of points. And so let me just go ahead and do that. So if I were to draw this line, let's say like that, then it's going to intersect it right here. Let's call that point B, and then you guessed it, that point is going to be C. Alrighty, so in elliptic curve cryptography, what happens is you have a curve that's defined by a math function, and then you have a starting point A, so I'll put A, and then you have this this idea of what's called a dot function, so I'll put dot, the dot function right there. Okay, so A dot something is going to yield a certain value. So if you dot A with itself, let's say I dotted A with itself and it yielded this, essentially you draw the straight line through the curve and it's going to intersect in these 2 points. So if I said A dot B, then that would yield C, let's say. So if I said A dot B, then it yields C. And then what you can do is if you want to do that dot notation again, then you can drop the value from C because of the symmetric property of this curve about the x-axis. You can drop it down to this, so it's the opposite value on the x-axis from C, and then you can draw A over to that point like that. And so let's say that this is a value D, and then you notice that it intersected again right here, and we'll call that value E. And then what you can do at that point, you can dot it again, and it's not a very good E. Okay, there's E. So you can dot it again and you can bring that up, and now it's going to intersect it right there. Then you can start back at A, you can go through that point, and then this thing just keeps going over and over, and you can dot it a certain number of times, and I'll say that we'll dot it n number of times. So A dot B, or A dot itself actually, n number of times is going to yield, let's say, a value, I'll call it Z. Alrighty. Another thing that I want to point out is that you have the concept of what we'll call a max value out here, and a max value on the x-axis. So I'll just put this max line out here. And if you can imagine, as you do this dot function or this dot notation over and over and over, some of these values that fall on the curve may go like way out here on the x-axis, like way out, crazy huge numbers. And so the idea is you can set a max, and if the value falls beyond the max as you're doing this dot notation, then you essentially take the value that would go beyond the max, you bring it back to the beginning, and you come over that far. And so the bottom line is you keep everything inside the max value. And so the max value, when you start talking about private and public keys in this public key crypto system, the max value is actually the key size. So I'm going to say key size equals max. Okay, so essentially what that does is it says, as you increase the key size in an elliptic curve crypto system, you have increased the amount of space that you're able to work with now on this curve, and you increase the amount of values that would be able to be used as points on this curve. So again, as the max goes out, then now you've got more points to work with. It becomes more difficult.
I just want to add one comment here. So you can imagine that elliptic curve is, I'm just giving a very informal comparison, right? You know, billiards table. Your billiards table is a table with where you have balls and you hit the ball and the ball will hit the walls again and it will reflect and it will reflect. And it will be within the space of the billiard, but it can hit the wall many times and then it will come to a final stage, right? Similarly, even in the elliptic curve cryptography, no matter what, how many times you perform this dot operation, which is like a addition, multiplication, you can say, and the values are reflected back onto the curve. So that is the main thing. I think we will watch for a couple of minutes and then we can discuss.
To you know, to undo this thing and to try to crack this whole thing. But of course, as Max goes out, you've got more numbers to work with, so you've got to crunch through all those numbers as well. So there's a give and take. All right. The other thing I was going to mention is the private key. So I'll put private over here. The private key in an elliptic curve crypto system is actually this n, which is the number, and I'll put dot right here. It's the number of times that you dot this thing with itself. So to kind of recap a little bit, public or elliptic curve crypto system, you have a function that's defined, or you have a curve, I'm sorry, that's defined by a math function. You have a starting point A, you have an ending point Z, and then you're going to dot this thing with itself a secret number of times, so an n number of times. And as it turns out, it's kind of interesting because if you are given the actual curve itself, the function that defines this curve, and if you're given the starting point as well as the end point on the curve, the Z point, as it turns out, it's extremely difficult to find out this number for n, the actual number of times that you dotted the function with itself to get to that point. And so that provides the basis for this trapdoor function to be able to say, hey, I can give you out public information to everybody, the starting point, the actual function that defines the graph or the curve, but I'm going to keep some stuff private, and that is this n number of times that this function is dotted with itself. Okay, so that's kind of the basics behind it. Of course, elliptic curve cryptography can get extremely complicated. There are, of course, more details to it than all of that, but this gives you kind of a basic understanding of what's going on, sort of behind the curtain of elliptic key or elliptic curve cryptography. And so, so anyway, as far as the big IP goes, really quick, we support, going back to that RSA versus elliptic curve, key size. The big IP supports both 256 and 384 size keys. So get out there, configure your big IP, offer up that elliptic curve cryptography to those clients. I'm sure they'll appreciate it because they got a lot less to deal with in terms of crypto, functions that they have to compute and all that. So, so thanks for tuning in today. Hopefully you've learned a couple things about elliptic curve.
This is one of the best videos I have encountered with elliptic curve cryptography, right? Like it's a bit very hairy math, you can say. It's very complicated math and things like that. I'm not going through all those things, but I'm trying to give an intuition how you can use elliptic curve cryptography and things like that. So this is the elliptic curve. For example, the Bitcoin uses what it is called SP 256K1. So this is the elliptic curve which we use. And the formula for elliptic curve is this one, right? Y squared is equal to x3 plus 7 and taken over FP, which is a big prime number and things like that. So again, it boils down to using the modular arithmetic. What is modular arithmetic? So for example, you take the mod values of each thing. And so for example, let's say you compute the mod 7, 16 over mod 7. So what you do is you divide 16 by 7 and it goes 2 times and the remainder is 2. So so we get 2 as the that is the mod value, right? So this is called the modular arithmetic. And the way to understand the elliptic curve cryptography is it is built over the modular arithmetic, and it offers very strong security properties. And I don't know how far you got, you understood from the video and things like that, but The main important concept here is the trapdoor function. Trapdoor function is the function which offers the security, right? So again, to give a very informal intuition about the elliptical cryptography, let me use a very stupid example, right? Let's say that you have a billiard table and you have only one ball on the billiard table, right? So, and you ask your friend to go and stay in a separate room where he cannot see the billiard table, and then you hit the ball. Let's say the ball hits the walls many times before stopping, and then you ask your friend to come inside and ask him to guess how many number of times the ball hit the walls, right? So of course, probably it is easy to guess, because if you use a billiard table, if you hit a ball on the billiard table, probably it doesn't hit the walls more than 10 times. Let's imagine that you have a very perfect no friction billiard table, and if you hit the ball, it will hit the walls several hundred times before stopping into a motion. And then it is very hard to guess how many times the ball hit the walls, because he is not observing the table, right? So that is the kind of trapdoor function functionality offered by the elliptical cryptography. So what normally we do is we take for example, G is the generator. This is the point where we start with, and then we take the tangent, and then we why tangent, right? So tangent is like adding the same point to the other thing. So you draw a tangent here, then it will meet here, and you will get 2G, and you take the reflection of it, and this is the result of G plus G, right? And similarly, you can take a tangent here, so then it goes to here, and then take the reflection of this one, so it is the 4G. So again, at this point, you take the tangent, and it will hit the curve here, which is the reflection of 8G. So you take the other point, it will be the 8G. So basically, you start with a generator function, generator value, which is G, and you multiply it many, many times. This is like hitting the ball many times the billiards walls without knowing that, right? And we keep track of how many number of times we did this addition slash multiplication, and that is our private key. And the final output value, which is the final output value, and the generator value, these are the public key properties. So if I go here, just one sec. Yeah. So let me roll back here. So here we have the generator function. So what we do is, when we use elliptical cryptography, we give the public key becomes the first of all, let us talk about the private key, right? The private key is the number of times we multiply the generator value by itself. Let's say that we multiplied the generator value 1024 times, then 1024 is our private key, and the final output value is the public key, right? So again, in the elliptical cryptography, we don't go with the small numbers. So that means my private key will be with a high mean entropy. So that means I will take the private key with from a pretty large number. So that means I start with G. Maybe I will multiply the G with, for example, 1 billion times or some billion times, so that nobody else can get it. And the output value is the public key. Any questions or comments and things like that? Did you get it, or are you completely lost with elliptical cryptography? Have you heard about elliptical cryptography before? Should K be the prime number? No, not necessary. It could be any number. So that is why one of the reasons why one of the recommendations when you use elliptical cryptography is, don't go for a very simple, very small K number, right? So for example, if you are lazy, and then if you choose a K less than 100, anybody can guess it, right? Because one thing you have to remember is this. Let me go back here. We clearly specify what is the elliptic curve we are using in this one. So in case of Bitcoin, you have this. This is the curve which is used. So everybody knows the starting number, which is the G. Which is the G. G is the generator function, and everybody has knowledge about G. So everybody knows that where you started, where is your starting point. Let me put it like this. Only people don't know how many times you added that number to it, right? So that is the K. So if you choose a K, a small number, for example, let's say that I am very lazy, I choose my K as 95, right? And if I give this information, if somebody knows that I have some coins at this location, public key, right? So the capital key, then they can, since they know the generator value, they can simply multiply the generator value with several numbers, and then before 100 they can crack my private key, right? Because I have chosen K as a small number, 95. But on the other hand, if I choose my private key, the number of times I multiply as, for example, 1,044,729 or something like that, right? And then of course, everybody knows the starting point, but they have to try these billion times to get to my private key. So that is the trapdoor function, which because it takes so much time and so much computational power, you have to try and try and try. So that is where these trapdoor functions are often in this one. Again, what happens if you get quantum computers? So that's an interesting question. When we get the quantum computers, you will, of course, some of the cryptographic functions might become vulnerable because you have a huge computing power in your hands and things like that. But on the other hand, cryptography is also progressing a lot. So we will get quantum resistant crypto systems in place by that time. At least we are also looking into quantum computing here at Copenhagen and Denmark. And to our estimation, probably we don't have any practical systems that can work reliably in next 20 years or something like that. So, okay, any more questions? Let me finish this slide and then we can take a break, right? So the video already compared beautifully between the RSA and elliptic curve based systems. You can see here, for example, in the symmetric encryption, a bit size of 256 bit size, AES or advanced encryption scheme, which is one of the popular one, or triple DES and these kind of things, they offer the highest security. You can see here, this is equivalent to 15,360 bits in the RSA or public key system. Whereas in ECC, it is equivalent to 512 bit computation. Of course, symmetry is very, very good when it comes to the security, but we have the key distribution problem. If you use symmetrically, you have to go and distribute the keys to everyone. This is like, let's say that you have, what is EDA? Where is the EDA? Elliptic curve. Where did you see that one? ECDA? Oh, I think it's a mistake. Yeah. Elliptic curve digital signature algorithm or something like that. So it's it should be like elliptic curve cryptography. So that's the reason why we don't go with symmetric curve. Because if you go with symmetric curve, let's say that you transferred your coins, you have to go personally and hand over the key to the person to whom you sell the coins, right? So that's why you don't use symmetric curve cryptography. But on the other hand, elliptic curve cryptography offers a much better strength when compared to the RSA algorithm. Okay, I think this is a very good introduction about the elliptical cryptography. Of course, there are a lot of videos, and if you want to know more about the math, then you can refer to the other aspects. So this is how we generate the public key. So you start with the generator function, and generator function generator value is known to everyone based on the curve you use, and you use the k is the number of times you multiply, and which is your private key. Okay, so let me finish this slide as well. So yeah, and yeah. So how actually these keys are used in the Bitcoin? Again, I don't know whether you were told that we use mostly two books. The one book is the Bitcoin by Arvind Narayan, which you might have seen in many places. It was referred on the slides. The another book is this Mastering Bitcoin, Unlocking Digital Currencies. And this is also a good book, which talks very practically about the Bitcoin programming and things like that. And you can get this book. It's available online and things like that, so you can easily find it out. And I normally put the page numbers, so most of the times the page numbers are located to that, and you can read further in the book. So the private key is 256-bit. So basically, it is the number of times we did that one. And public key is 512 bits, uncompressed. And then you will do some operations on the public key, and then you get it like this. So this is how we do it, right? So the public key, we get it as the 256 and then hash it. And then we do hash 160 to get it to 160 bit and bit where hash will digest and things like that. And then you get 20 bytes, which is 166 bit. And then you encode with the base 6058 check. What does it mean? So when you do these encryption and hash values, you get the numbers which are not how can I say ASCII values. So what is ASCII values? ASCII values is like A to Z and numbers and human interpretable signals, right? Many times in the crypto systems, when you do and perform encryption or other kinds of things, you get the binary values, you can say, like EXEs are contained binary values. So you convert the binary values into some visible format. So when you do base 68 pair encoding, so you will get a value like this, 17J. So it will map all the binary values outside the ASCII region to some sort of the values here. So that's how the base 58 check will work. Finally, you will get a public key like this. So all these things behind it happens. Okay, so and then it uses elliptic curve cryptography. Is there a question? Okay, and then one important message is good randomness is essential. So the k value should not be the small, right? If you choose a small k value, then it is easy for people to guess it. Okay, let's take a break here, 10 minutes break, and then we will join you. We will join in 10 minutes. I will close the session, but I will keep the session open. I will leave now to save the recording and then see you in 10 minutes. Okay. Let me stop share. And,